Welcome to this course information video on CS370 Numerical Computation. My name is Christopher Batty, and I'm a professor of computer graphics and scientific computing in the School of Computer Science at the University of Waterloo. And I often teach CS370. Now, if you're thinking about taking CS370, the first question you might have is, what is numerical computation? Well, it's the design and use of computer algorithms to approximately solve problems of continuous mathematics. And this covers a very wide swath of material. In this course, we're going to consider representing and manipulating real numbers approximately. We'll look at fitting, manipulating, and analyzing different kinds of numerical data in a variety of ways. We'll look at solving ordinary differential equations, again, approximately. We'll look at solving certain linear algebra problems, such as linear systems of equations. And we'll try to understand various properties of numerical problems and algorithms, and in some cases, how they differ from the corresponding analytical or continuous mathematics. So why would you care about numerical computation? The main reason is that it enables solving problems in a huge range of practical domains. And I've shown a couple of images here, kind of giving you a sense. And let's just talk about a few of them. So weather and climate modeling, such as you see on the bottom left image. Financial modeling, such as in the middle left, prices and stocks and so forth. Physics and chemistry, almost all of, or many aspects of physics and chemistry can be described through differential equations. My area of expertise is visual effects and computer animation, and I've included an image from the movie Avatar 2 on the right-hand side there. Machine learning, neural networks, computer vision, all of these things fundamentally involve working with real numbers and continuous math. Many engineering applications involve numerical computation, such as the, landing gear of an airplane that I'm showing in the top left there. We're visualizing the airflow around those structures. Architectural design, such as this building in the top right from the York University campus. Biology, such as modeling organs, disease spread, population growth, etc. Image, video, and sound processing. Search engines, recommender systems. Really, the list goes on and on and on and on. Anywhere you encounter real numbers in the real world and have to solve mathematical problems, typically you're going to be doing numerical computation. So I'll talk a little bit about the course structure. In the first week, we'll look at floating point numbers. In the second week, we'll move on to interpolation and splines for 2 weeks. Then we'll look at ordinary differential equations for about 3 weeks. Then we'll look at Fourier transforms for 3 weeks, and finally numerical linear algebra for about 3 weeks. And over the course of the term, there'll be 4 assignments. Each of those would involve some mathematical kind of pencil and paper questions, and then application-oriented programming tasks to try and give you a sense of how a lot of these tools are actually used in practice. And the course will also have a midterm and a final exam. So I'll talk about each of these course topics to give you a sense for what you can expect. So the first question is, how can we digitally represent the real numbers R? Because they are infinite. They're both infinite in terms of the number of decimal digits, and they can get infinitely large and infinitely small. So of course, we have finite amount of memory and storage on our computers, so we can't work with the real numbers. So what do we do instead? And the answer is we use floating point numbers. We want to answer questions like, how does this representation affect our calculations, and what kinds of errors can be introduced? And you might expect that these errors would be relatively small, and in some cases they are, but they can have disastrous effects if we get them wrong. So a simple example here is from computer graphics, again, a simulated piece of cloth. If we don't take great care dealing with the errors induced by floating point representations, or approximation of the real numbers, we can have errors like these, this cloth intersecting through itself, which is obviously bad in most cases. Then we'll move on to interpolation and splines. So the question here is, if I give you a set of discrete data points, again represented as real numbers, how can we fit a smooth function that goes through or near those data points? And then how can we interpolate to generate new data points from that function? And we'll look at an application to curve design. So if you give a set of points in the 2D plane here, and you just tell me what the order of those points should be, I can fit a smooth curve that goes through those points. In this case, to spell out the word CS370 in some nice curly handwriting. Just to give you an example of where this kind of thing gets used in the quote-unquote real world, here's an image of Woody from the Toy Story movies. And you can see in the image here, Woody is kind of modeled as this polygonal, kind of piecewise linear surface. But the final smooth surface is generated by smoothly interpolating So you can see in the bottom right here, Woody has nice, smooth rounded features instead of the sharp polygons you see on the larger image. And this same kind of technique is used in computer-aided design for designing vehicles, products, planes, buildings, and so forth. The next topic is ordinary differential equations. So ordinary differential equations, depending on how much you've seen them in the past, they relate a function to its derivatives, and they're often used to predict how certain quantities change over time, such as temperature or financial values or speed or what have you. And the reason we care about doing numerical computation on these things is that they seldom have exact analytical solutions. So that's why we're going to develop computational solutions instead, or numerical solutions. So that's the answer to the question, is how can we approximately solve such equations? And examples come again from many, many domains, things like population growth, disease spread, predator-prey dynamics, most of physics, financial markets, and so on. And in this course, we'll look at an application to projectile motion, such as in the old video game Angry Birds. So here's a fun example that goes well beyond what we'll see in class, but just to give you an idea of the fact that ordinary differential equations can be used to solve very large-scale, very complicated problems, such as this massive pile of deck chairs accumulating on the ground. So again, the key here is to solve these techniques very efficiently and at very large scale in this case. The next topic is Fourier transforms, and the core idea here is that we want to be able to represent functions or data as a sum of many sinusoidal curves, and by doing that, it lets us achieve surprisingly useful processing. So again, we'll look at applications to image or audio processing. Here is 2 sine waves added together, but obviously real data is much more complex than that. So we'll look at things like image compression, where you can see here a bitmap image on the left with all of the data stored, a compressed image in the JPEG format, which uses Fourier ideas, and then an even more compressed image that reduces the image size down to 19 kilobytes. Lastly, we'll look at numerical linear algebra, which comes up in a vast range of application domains. We'll look at solving systems of linear equations, factoring matrices, and solving eigenvalue problems. And the application domain we'll look at here is ranking web pages. So Google's original PageRank algorithm allowed them to rank websites by considering the links between pages as indicative of quality or importance. And by converting the structure of those links into a huge matrix and solving an eigenvalue problem, they were able to rank web pages in a more effective way than previous algorithms were able to. All right, so that gives you a whirlwind overview of CS370 numerical computation, and I hope I'll see you in the class. Thanks very much.